Hi, I'm Jim Burnham. Welcome to General Chemistry. Today we're going to be talking about chemical reactions. In 1937, the airship Hindenburg was about to land in New Jersey after crossing the Atlantic, as it had done uneventfully many times. Suddenly, it erupted into a fireball as the hydrogen inside burst into flames. The chemical reaction that caused the disaster can be described rather simply as, and here's the disaster: hydrogen combines explosively with oxygen to produce water. We can describe this chemically as 2 parts hydrogen combined with 1 part oxygen to make 2 parts water. We are surrounded by chemical reactions. Cooking is a chemical reaction. Digesting food that we cook is a photosynthesis. Car batteries, car combustion, as cars burn gasoline. Rust. All these chemical reactions involve a change of substance, one thing changing into another thing. So we're going to talk today about how we describe chemical changes. We need to be able to describe chemical changes in writing. Remember, in our second chapter, we had a shorthand method for describing chemical reactions, right? It was reactants yield or produce products. But we're going to expand on that a little bit. Remember Dalton's atomic theory about chemical reactions? As reactants are converted to products, the bonds holding the atoms together are broken and new bonds are formed. The atoms are neither created nor destroyed, they are simply rearranged. So here is that same chemical reaction, 2 hydrogen, those bonds are broken, the bond between the 2 oxygens are broken, and then the atoms are rearranged to become water. This explains the law of conservation of mass, that all the atoms in the products are the same atoms that were present in the reactants. They're just arranged differently. They're neither created nor destroyed. You can't add them, you can't subtract them. So how do we write chemical equations? A chemical equation, remember, is a concise representation of a chemical reaction. And so here are the parts of a chemical equation that we're going to look at. The stuff on the left of the arrow is the reactants. That's the chemicals, the elements, the compounds, the molecules, whatever, that exist before the reaction. In this case, this is the decomposition of water. So this is the reverse of the Hindenburg. So reactants on the left, products on the right. Coefficients to indicate more than one molecule. So here we're taking 2 molecules of water, we're decomposing them into 2 hydrogen molecules and 1 oxygen molecule. Now, just as writing a sentence is governed by certain rules, for example, you have to have a subject and a verb, you have to start every sentence with a capital letter, you have to end with some sort of punctuation mark, right? So too, writing a chemical equation is governed by rules. The equation must have products and reactants. It must follow the law of conservation of mass. So we can describe chemical reactions in different ways. So this is the chemical reaction known as rust, the formation of iron oxide. So a word equation would be this: iron plus oxygen produces iron 3 oxide. A chemical equation for the same thing would be iron in the symbol plus O2 yields Fe2O3. Now this is known as a skeleton equation, this last equation. You'll notice here that there's 1 iron on this side, but there's 2 iron in our product. We start with 2 oxygen here, we end up with 3 here. So this is obviously not balanced, but it's okay. This is known as a skeleton equation. It represents the bones of the chemical reaction, but doesn't show the relative amounts of the products and reactants. Just says, hey, we have some iron reacting with some oxygen to produce iron oxide. So that's the hallmark of a skeleton equation. They are unbalanced. So if we combine, let's say, hydrogen and oxygen to make water, as you can see here, the hydrogens are balanced 2 and 2, but you have 2 oxygen here, only 1 here. That's not balanced. But skeleton equations are an important first step to getting the correct full balanced chemical equation. Now, to a chemical equation, we can also add physical state. So we can say iron in its solid state, solid iron, plus O2 in its gaseous form, gaseous state, forms iron oxide, another solid. In many chemical reactions, we sometimes add a catalyst, and that is something that speeds a reaction up without itself being used up. So it helps the reaction move along more quickly without itself being consumed by the reaction. So here is a pretty famous reaction called elephant toothpaste. It's the decomposition of hydrogen peroxide. And this, over time, this reaction happens, but it happens very slowly. It can take months for hydrogen peroxide to break into water and oxygen. But with a catalyst, the reaction can proceed very, very quickly, sometimes even in a matter of seconds. So catalysts never produce more product, but they produce the same amount of product more quickly. So this is how we would indicate if we added, for example, manganese oxide as a catalyst to our decomposition of peroxide. We put it right over the arrow. Because it's not something that is used up, and it's not something that's produced, but it is something that speeds the reaction along. So that's where we stack it. We stack it right over the arrow. So here are some symbols that we'll use in chemical equations, right? The plus sign that separates, so if I have 2 reactants or 2 products, so anytime I have more than one thing, I use a plus sign. Here's yields or produces. This is, we can replace an arrow that indicates that the reaction is going in one direction with a reaction that is a reversible reaction. This designates the state of the reactant or the product, solid, liquid, or gas. This tells us we have an aqueous solution, that whatever we're talking about has been dissolved in water, and we put that right after the formula. So if we took salt, NaCl, and we dissolved it, then it would be NaCl aqueous, so dissolved salt. Okay. A delta over the arrow, or the word heat over the arrow, indicates that heat has been supplied to the reaction. And as we said before, something written above or below the yield sign indicates that it is a catalyst. In this case, platinum is a catalyst, maybe in a catalytic converter or something. So the key concept is equations must follow the law of conservation of mass. Whatever you have on the left, you have to have on the right. So how do we balance chemical equations? How do we go from an unbalanced skeletal equation to a balanced chemical equation? Okay, let's just look at something simple. Let's say we're building a bike. The word equation for this might be take a frame plus a wheel plus a handlebar plus a pedal, and you get a bicycle. So if we turn that word formula into symbols, we might use F, W, H, and P. And then our skeleton equation would be take an F and a W and an H and a P, and it will yield an FW2 and an HP2. Now why here? Well, because a bike, a full bike, has got 2 wheels and 2 pedals. So now that equation is our skeleton equation, but it's not quantitatively right. It doesn't show the quantity of the parts needed, right? I show 1 W here, but I need 2 W's in my finished product. I show 1 P here, but I need 2 P's in my finished product. So in a balanced equation, each side of the equation has the same number of atoms or parts or whatever of each element. So that's the key, the same number of atoms of each element on each side of the equation. So back to our bike example, to balance this out, we would say 2W plus 2P plus F plus H gives us FW2 HP2. It's balanced this time because it gives the correct quantity of each reactant and each product. The numbers in front of the symbols that we saw there, we're going to call those coefficients. If we don't put a coefficient in front of a number, we assume that it's 1. Now, why do we have to balance? Right? The law of conservation of mass. We can't just invent atoms out of thin air or disappear them if we don't need them. Right? We have to account for all the atoms on both sides of the equation. So here's an illustration of the law of conservation of mass. If you took 100 grams of mercuric oxide and you decomposed it, you would get 93 grams of mercury. You would get 7 grams of oxygen, and together they would equal your starting. So again, whatever you start with, you have to end with, even if it's rearranged. So the mass will be conserved. Therefore, every atom is conserved. So again, a balanced equation means that each side of the equation has the same number of atoms of each element. So here are some basic rules for balancing chemical equations. The first thing that you have to do is determine the correct formulas for all the products and reactants using what we know about elements and compounds. We write the formulas for the reactants on the left, the products on the right, with a yield sign or produces sign in between. If 2 or more products are involved, we separate them with plus signs. This is our skeleton equation. And now we have to balance. So all you do is you count the number of atoms of each element in the reactants and products. And if you have a polyatomic ion unchanged on both sides, just keep that as a single unit. So if you have a carbonate on one side, keep it, and a carbonate on the other side. Don't count all the little C's and O's, just count the carbonate as a whole. Balance the elements one at a time using coefficients. It's helpful to begin with elements that appear only once on each side of the equation. Remember, do not change subscripts. That might be tempting, but you can't do it. A change of subscript is a change of substance. Check each atom or poly to make sure the equation is balanced, and then finally make sure all the coefficients are in the lowest possible ratio that balances. All right, so here's how we would do this. Here's our word equation. Methane combines with oxygen to produce carbon dioxide and water. So these are the reactants. They're going to be on the left-hand side of the arrow. These are our products on the right. We'll turn these into symbols, and we will balance. So our balanced chemical equation is CH4 plus coefficient 2 oxygen yields 1 CO2 and 2 waters. And here is an atomic model just to illustrate this. And you can see here you have 4 O's in the reactant side, 1, 2, 3, 4 O's on the product side. Okay, 1C, 4 H's, 4 H's. This equation is balanced. Now let's look at the different types of chemical reactions. We're going to see in this chapter that we're going to look at 5 different types. These aren't the only types, but these are 5 main types of chemical reactions. And so instead of memorizing millions of different chemical reactions, you can classify those millions under these 5 general types, or at least these 5 will classify many of those millions of reactions. So remember, in Chapter 6, we learned to name millions of chemicals by following a system of naming. Well, we can also look at patterns of chemical behavior that let us predict the products in many reactions. And so these are the 5 different types of chemical reactions. Combination, sometimes known as synthesis, you're making something. Decomposition, you're unmaking something. Single replacement, double replacement, and combustion. We'll go through each of these carefully. So let's look at the first one, combination or synthesis. In a combination reaction, 2 or more substances combine to form a single substance, a new single substance. So here we have magnesium combining with oxygen, producing magnesium oxide. Mg plus O2 yields MgO. Now this is the skeleton equation. It's not balanced because here, look, I have 2 oxygen here, only 1 oxygen over here. So I've got to balance that up. Well, when I balance my oxygens by adding a 2 here, then I've got to add a 2 in front of my magnesium, and now with these new coefficients, I have a balanced chemical equation. Now, the most common combination reactions are either 2 elements or 2 compounds. And the product is always a compound, right? Because we're making it out of 2 separate elements, 2 separate beginning components. What determines if that compound is ionic or molecular? Remember, we learned about how to name ionic compounds and molecular compounds. What's the type of reactants used? If we're making something out of a metal and a non-metal, it's going to be an ionic compound. If it's made out of 2 non-metals, it's going to be a molecular compound. So potassium reacts with chlorine to form an ionic compound. You have a metal and a non-metal. So we can write the correct formula for the product by considering the charges of the anions and cations. So in this case, we have potassium combining with chlorine to make KCl. That's our skeleton equation, but it's not balanced. We do know that we have these are going to be this is balanced in this formula unit because we know that this +1 of the potassium is balanced out by the -1 of the chloride. But look, we have 2 chlorines here, only 1 here, so we got to balance it up. We got to put a coefficient of 2 in front of the KCl. That means we got to have a 2 in front of the K. Now, 2 Ks on this side, 2 Ks on this side, 2 Cls on this side, 2 Cls on this side. It's balanced. Now, let's look at the second type of chemical reaction, and that's known as decomposition. So this is going to be the opposite of composition or combination. We are going to take a single compound and then break it down into 2 or more products. And that can be a combination of elements and compounds. So this is the opposite of composition or combination or synthesis. So in this case, we are going to take water and we are going to decompose it. We're going to deconstruct it, separate these bonds and turn it back into the diatomic molecule called hydrogen and oxygen. Here is another decomposition reaction. So we have calcium carbonate, which is a solid. We add heat, and it decomposes into calcium oxide and carbon dioxide gas. Extremely rapid decomposition that produces gas and heat is known as an explosion. So that's what causes an explosion. A simple decomposition reaction that quickly produces gas and heat, and that expanding gas and heat tend to rip things apart around them. So here is a dynamite explosion, TNT. And the decomposition of trinitrotoluene, which is this big fat molecule here, notice that 2 moles of this TNT produce 3 moles of nitrogen gas, 7 moles of carbon dioxide gas, and 5 moles of water gas. So from 2 moles, we get a total of 15 moles of gas produced. And that is a very, very energetically powerful reaction. And that expanding gas is what creates all the damage of dynamite. All right, the third type of reaction is known as a single replacement reaction. In a single replacement reaction, one element replaces a second element in a compound. So here diagrammatically, it will look like this. So A is bonded with B, and along comes C, and C is going to replace A. C is going to kick A out of its bond with B, and now C is going to take A's place. And so now you have C and B, and A goes home alone. It's similar to a man cutting in on another man at the dance floor. So at the start of the dance, dancer A is by himself, dancer B is with his hottie. Dancer A cuts in on dancer B, displacing him or replacing him, and now dancer A is dancing with C, and B is going home alone. A great example of a replacement reaction, a single replacement action, potassium reacting in water. What happens is that the K here is going to replace one of these H's in the water. It's going to kick that H out and take its place, and then those hydrogens, those replaced hydrogens, are going to combine and bubble out as a gas. So this is my meme for a single replacement reaction. Here's the metal you came with. Here's the metal you leave with. This metal replaces this metal. Now, whether one metal will replace another metal or not can be determined by the relative reactivities of the two metals. And that leads us to what is known as the activity series of metals. Some metals are more reactive and some are less reactive. And so we normally compare them to hydrogen. Will a metal displace hydrogen like potassium displaced the hydrogen in water, or will it not? So metals that are above hydrogen are more reactive. And here's how you read this. Any metal above another metal will replace it in a single replacement reaction. So magnesium will replace zinc. Zinc will replace tin. But tin will not replace iron. It's the higher ones can replace the lower, but not vice versa. A reactive metal will replace any metal listed below it in the activity series. So, will magnesium replace zinc in this compound of zinc nitrate? It will, because when we look at magnesium in the activity series of metals, it is above zinc. So magnesium will kick zinc out. Bye-bye zinc. Will magnesium replace silver in a compound of silver nitrate? Well, let's look at, magnesium is way above silver. Of course it'll kick it to the curb. Will magnesium replace potassium in a potassium nitrate compound? Well, no. Magnesium is below potassium. It will not displace potassium, so that reaction will not happen. So we can see how an activity series will help us predict whether or not one metal will replace another, and thus whether or not we'll have a single replacement reaction. In nonmetals, you can also have replacements, but it is usually limited to the halogens. And in this case, when you look at the halogens that are at the top of the chart will generally replace the halogens below it. So fluorine will replace chlorine, which will replace bromine, which can displace iodine. So sometimes you'll see the activity series like this. Here's the one for metals, and then here's the one for halogens. Again, fluorine is at the top, iodine is at the bottom. Again, anything above will replace anything below, whether it's a metal or a halogen. The fourth type of reaction is known as a double displacement. So just like we saw in single displacement, where one metal replaces another metal, or one element replaces another element, here we're going to have a double switch. It's an exchange of two positive ions between the reacting compounds. So single displacement was a displacement of a cation by a metal. Here now we're going to have an exchange of both cations. So here's what it looks like. All right, so A shows up at the party with B, C shows up to the party with D, but A and C switch partners. So C comes over here to dance with B, A switches over here to dance with D, and that's the way they go home. Okay? So the cations switch their positions with respect to the anions. That's a double displacement reaction. There's lots of ways you can show this diagrammatically, but the easiest one for me is just to take one cation, swap it out, so stack this sodium in front of the nitrate, and then replace the silver in front of the chloride. A double displacement reaction usually takes place between two ionic compounds in aqueous solution, in a water solution, being dissolved in water. And it often produces a precipitate, something that goes from being in solution, being dissolved in a solution, to being unable to stay dissolved. That word is known as insoluble. So if it's insoluble, it will fall out of solution, and it will trickle down or fall out as little flakes or little solids, and they will fall down to the bottom of the container. That's a precipitation reaction. So here is a classic example. This bright yellow solid is coming out of solution as the result of a double displacement reaction. So again, a precipitation reaction occurs when dissolved substances react. In this case, they do a double displacement, and then one or both of the products is no longer soluble. So here we have lead nitrate combining with potassium iodide, and what you're going to see, the Pb is going to replace K and become PbI2, and the K is going to replace Pb and become KNO3. And what happens is the KNO3 is still in solution, that doesn't fall out, but the PbI, notice here, with an S, means it is no longer aqueous. So start aqueous, 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 no longer aqueous. It will fall out of solution. It will form a precipitate, a solid product. So for a double displacement reaction to occur, usually one of the following is true. One product is only slightly soluble and therefore precipitates or falls out of the solution. So in this case, here we have sodium sulfide plus cadmium nitrate. They're going to do a switcheroo, right? The cations are going to replace each other in this double displacement. CD is going to go over here with S, Na is going to go over here with NO3, the nitrate, and we're going to get a yellow precipitate because while this stays soluble and dissolved, this is insoluble, won't stay dissolved, drops out of solution as a yellow precipitate. So another thing that can happen, so the first thing that indicates a double displacement is the formation of a precipitate. Another thing that can indicate a double displacement is a gas that is produced and bubbles out of the mixture. So here we have, again, two compounds, sodium cyanide and sulfuric acid. And what we're going to see is that the H and the Na are going to displace each other. They're going to replace each other. So H is going to come over here to form HCN. The Na is going to come over here to form Na2 sulfate. And this is a gas. And this will come out of the aqueous solution. This stays in aqueous solution. It stays dissolved. Don't see it. No change. No detectable change. But this bubbles out of solution. So if you form a precipitate, indicates a double displacement. If you form a gas, indicates a double displacement. And the third is one of the products is a molecular compound like water. So in this case, we have calcium hydroxide combining with HCl, and the H and the C are going to displace each other, and it's going to form, when this H goes over here, it's going to form water. So those are the three ways we can detect a double displacement reaction: the formation of a precipitate, formation of water, and the formation of gas. The fifth type of general chemical reaction is known as combustion. Combustion is very familiar to us, right? Fire burning is combustion. Flicking a lighter is combustion. Burning anything is generally a combustion reaction. And what we mean by that, we define a combustion reaction as an element or compound reacting with oxygen, often producing energy as heat and light. Think of a fire. What does a fire give off? Pretty light, lots of heat. Combustion reactions commonly involve hydrocarbons, that is, compounds built out of carbon and hydrogen. And if we have what's known as complete combustion of the hydrocarbons, the products will be carbon dioxide and water. That's important to remember, because if you can have complete combustion, as the word indicates, it seems like you could also have, as we're going to see, incomplete combustion. So here is a hydrocarbon. Looks like methane, and we're combining it with excess oxygen, so plenty of oxygen to go around. We'll see why that's important. Okay, we burn this, and it produces water and carbon dioxide. If there isn't enough oxygen to completely react with the fuel, you get what is known as incomplete combustion. And incomplete combustion, caused by a lack of O2, if you burn hydrocarbons with incomplete oxygen, a lack of oxygen, you start to get carbon monoxide instead of carbon dioxide and water. And you can also produce carbon in the form of soot. So remember, in complete combustion, we get water and carbon dioxide. In incomplete combustion, we get carbon monoxide, carbon, and water. The difference is a big difference because carbon monoxide is deadly gas. This is why you're not supposed to burn certain things inside a house, like propane, because if you have a tight room with no ventilation and the oxygen drops too low, you will go from complete combustion in the beginning to incomplete combustion. You can produce this deadly carbon monoxide, and it can put you to sleep and you just never wake up. So a reaction between some elements and O2 is also an example of a combustion reaction. Remember, combustion just means reacting with oxygen. So if we take magnesium plus oxygen and form MgO, that is a combustion reaction. But notice too, it's also a combination reaction, right? I'm taking an A and a B and I'm making AB. So we can classify the same reaction sometimes a couple of different ways. Again, here's S plus O2 making SO2. Again, we call this combustion because it's reacting with oxygen, but we also call this a combination reaction. We're making a new compound from these simpler elements. Okay, how do we predict the products of a chemical reaction? Well, once we know these 5 kinds of chemical reactions, we're going to see, hey, if you're starting with 2 elements and you get a reaction, that's probably a combination or a synthesis reaction. If you start with 1 compound and you get some products, that's going to be decomposition, because you don't have anything else to work with. If you start with a compound and 1 element, then you might look for a single replacement reaction, or possibly, again, synthesis. If we have 2 compounds, we can think of either synthesis or perhaps a double displacement if we have precipitation, gas forming, or water forming. And if we have a hydrocarbon combined with oxygen, think combustion. Think combustion. All right, so here's how we represent this generically. Right? A synthesis reaction is A plus B equals AB. Okay, you're going to start with 2 or more substances, you're going to get a compound. Combustion, you're going to start with a metal, or a nonmetal, or a compound, and then in all 3 cases you're going to add oxygen. And this can create the oxide of the metal here, the oxide of the nonmetal, or 2 or more oxides. And here's the general combustion equation. A plus O2 yields some sort of oxide with A. Decomposition, you're going to start with 1 compound and then produce 2 or more elements or compounds. AB decomposing to A and B separately. Single displacement, you're going to start with a metal in a compound or a non-metal in a compound, and the new compound will be produced with a replaced metal, or a new compound will be produced with a replaced non-metal. So basically, A comes in here with BX, kicks B to the curb, and AX go home from the dance. Double displacement is you start with two compounds, often in aqueous solution, and you get two different compounds, one of which is a solid, water, or gas, as a sign of the double displacement. Now, we mentioned reactions in aqueous solution. Why is that important? Well, we live in a water-based world. 70% of the Earth's surface is covered by water. So we would expect water to be very ubiquitous, and it is. We ourselves are up to 65% water. So water is hugely important, and so it shouldn't surprise us that many important chemical reactions take place in water, and the fancy name for that is in aqueous solution. Many things dissolve in water, and therefore many reactions take place in water. So that takes us to the concept of net ionic equations. So let's look at the double displacement reaction. Silver nitrate plus sodium chloride. Okay, the sodium and the silver are going to, the cations are going to replace each other. So you're going to get silver chloride, a solid that's going to precipitate out, and then sodium nitrate, which is not going to precipitate out. It's going to stay in solution. Now, here's the interesting thing. What happens when these ionic compounds dissolve in water is that they don't stay connected to each other. So the more accurate way to write ionic compounds when they're dissolved is to write them separated. So in water, right, the silver and the nitrate are going to separate, cation, anion, and the sodium and the chloride are going to separate into their respective ions. And then, in the case of the silver and the chloride, they're going to recombine as a new ionic compound, and that's going to drop out of solution. But the sodium and the nitrate, we say that they're now together, but there's really no evidence that they're together because they're still dissolved. I mean, they're the two left, on the other side of the dance floor, but that doesn't mean that they're dancing. These two are dancing. These two are just hanging out. So this is known as the complete ionic equation. So we're writing this equation, we're rewriting it as the ionic parts, because that's what happens. Ionic compounds separate into their specific ions. Now, there's one more thing. We can now look at this complete ionic equation, and we can notice that, hey, look, nitrate is alone on the left, and it's alone on the right. And sodium is alone on the left and alone on the right. Nothing happened nothing changed about nitrate, nothing changed about sodium. And so we can actually eliminate them as spectator ions. They're just standing there watching the action. What's the action? Silver is getting together with chloride to form a new compound. These guys are going to the altar and getting married, and these guys are just like, okay, good luck, right? So we can, in this reaction, we can eliminate the spectator ions by crossing them out, and that gives us what's called the net ionic equation. Because the net ionic equation here is that Ag plus got together with Cl minus to make AgCl a solid. And it precipitates, falls out of solution, and that's the headline. So we're going to leave out the non-news-making items, the spectator ions, because nothing happened with them, nothing changed. Here's where all the action was. Silver combined with chloride to make silver chloride. So the net ionic equation just leaves the particles that actually do something in the reaction, that actually change. Spectator ions are like going on a double date, hey, and then watching while their partners get together and dance. Right. They are left out of the equation. So when we write net ionic equations, we also have to balance the ionic charges if they are not balanced. Now in this case, you have a plus and a minus, and then over here, in this formula unit, right, we would think of this as one plus and one minus. So the pluses and minuses on the left equal the pluses and the minuses on the right. They're balanced. But look at this reaction. Okay, so this is a single displacement reaction. We have lead coming in here, kicking silver to the curb, and going home with nitrate. But when we rewrite this as a net ionic equation, right, we see that nitrate is a spectator ion, so we get rid of it. And so what really happens is you start with lead as a solid, and it combines with silver, or it reacts with silver in such a way as to create silver as a solid. So remember, lead started as a solid, silver started to dissolve. Now lead is dissolved and silver has been precipitated out. But notice there's a +1 on the Ag and a +2 on the Pb. This is not balanced. You can't have a disparity of charges here. So the way to fix that is to put a coefficient in front of the Ag to give us 2 pluses on the left that balance out the 2 pluses on the right. So that's what we do. Coefficient here, giving us 2 plus charges on the left and yielding 2 plus charges on the right. So of the 5 types of reactions we've looked at in this chapter, both the single and the double displacement reactions can be rewritten as net ionic equations. So remember that. Those two, if it involves an ionic compound or compounds and some sort of reaction, you can usually rewrite it as a net ionic equation. Now we keep talking about the formation of a precipitate. Do we have any rules that allow us to predict the formation of a precipitate? I mean, as we saw, if we mix 2 solutions of ionic compounds, we can sometimes get the formation of an insoluble salt called a precipitate. So leads us to a couple of questions. What is a salt? I've used the word salt here, right? An insoluble salt. Well, a salt in chemistry is an ionic compound. It's any compound composed of a metal cation and a non-metal anion. So if you see the word salt here, don't just think table salt. Yes, sodium chloride is a form of this salt. It's an ionic compound, but it's not the only ionic compound. Every ionic compound is called a salt. And some of those salts will precipitate and some of them will not. So we need some rules to tell us that when that'll happen. And here are 5 rules, and these are all worth knowing, but I'll break it down more simply. But here they are. Let me go through them quickly. All nitrates are soluble. So all nitrates are soluble all the time. All ammonium, that's this poly, or group 1 metal compounds, called the alkali compounds, are all soluble. So if you see anything built out of nitrate or ammonium or any of the group 1 metals, they're going to be soluble. We're going to see that carbonates, phosphates, and hydroxides are generally insoluble unless they're hooked up with these group 1. So group 1 can overcome the insolubility, the normal insolubility of these. Bromides, chlorides, and iodides are generally soluble except when silver, lead, or mercury are around. And sulfates are generally soluble with certain exceptions. So I'll simplify these. Now, those 5 are worth knowing. But if you want a shortcut, think SPAN. SPAN. All sodium, potassium, and by extension, all group 1 metals, all ammoniums and nitrates are soluble. SPAN. Sodium, potassium, ammonium, and nitrate salts. Salts, ionic compounds, are all soluble. Okay, so let's sum it up. Why must chemical reactions be balanced? Well, because in a chemical reaction, atoms can't be created or destroyed. The law of conservation of mass says that all the atoms present in the reactant side must also be present on the product side. What are the 5 main types of chemical reactions? Well, combination, A plus B equals AB. Decomposition, AB breaks down into A plus B. Single displacement, one metal kicks out another metal from an ionic compound, sending that other metal to go home alone. Double displacement, the cations exchange places. Combustion reacts with oxygen. Okay, and here are some diagrams, okay, right? A plus B making AB, combination. AB being cut back into its parts, decomposition. Notice these are inverse reactions, right? Combination makes something, decombination unmakes it, decomposition. Okay. So in this case, C is going to kick out B and go home with A. In this case, A and C, the cations, are going to exchange places. What is the activity series and how is it used? Remember, the activity series of metals is a list of metals in order of decreasing reactivity, and they will tell us whether a single displacement reaction will occur or not. Metals high on the reactivity scale will displace any metal below it, but not vice versa. So when we look at this, lithium is the most active, gold is the least active. Anything high will replace anything low, but not in reverse. And likewise in the halogens, the higher halogens will replace the lower halogens. All right, that's it. Thanks for your time.